All right, guys. This is the last session that we have in this series of the Data Science Masterclass. The problem we're going to try to solve today is one that is slightly, different than what we have been doing so far. So let us maybe go to our whiteboard and see what we have completed up to now. So, so far we've talked about, within the data science space, if you want to understand a situation, then you would go down descriptive data science. And we did a little bit of exploratory data analysis with Power BI in our first session. And then we quickly went into the predictive space, right? The predictive space, we are just trying to make a prediction, and we're trying to take history and project that into the future. And this area is what typically when people say machine learning, that's what they're talking about. Then we went into, if we have data that is labeled, then we go down supervised learning. If the target is continuous that we're trying to predict, then we go down the regression path. And then if we know the relationships, if we don't know any, if we know that they are linear relationships, we can go down linear regression. If it's unknown, then we go down decision trees and we ensemble them either randomly or using gradient descent. On the other hand, if the target is discrete, then we go down the classification path. So it's either binary or a certain number of classes. And then we have a number of tools here. If we know that the features are independent, we can do a quick naive Bayes, which, like I said, was more of a probability calculation as opposed to a learning method. But if we can't assume independence, then we go down logistic regression. And if the data has many outliers, we might even try SVM. But all of these are simpler models. If the problem is more complex, like visual recognition, which with many features, then you might want to consider neural networks. And then a neural network with multiple layers would be a deep network. And then you have a few more special cases of neural networks that we could go down, right? If we go back up and say, all right, no, our data was not labeled, then we are in the unsupervised learning space. And if we, within unsupervised learning, if we are trying to determine relationships between rows, so every row is a data point, and we want to find relationships between the rows, that's what we call clustering. Within that, if we have a very large data set, typically, and we have to set the K, how many clusters we have, we can go down K-means. If the data set is smaller, we can try hierarchical, which basically creates every cluster all the way up to the top. And then when we have anomalies in the data set, then we would want to go down the DB scan path, okay, where we are clustering and at the same time detecting anomalies. If we're not really looking for relationships between the rows, then we can go down and create relationships between the columns and between the rows and the columns. This is what we talked about association last time. We built association rule mining whenever we wanted to try to figure out what items get bundled with each other. And so let's complete this view here with the other tools that we learned. So let's add, so within the association rules, we also have, so whenever this is, when we have data where by session or by transaction, then we would apply association rule mining. But when we have data that is across sessions, that means, over time we've collected data for the same user across multiple sessions, then we would call this as, recommender systems. And within recommender systems, if we don't have any user behavior data, so we are mostly talking about based on general content. So this is, if we only have general content data, then we would perform what we call the content-based filtering. But if we do have user behavior data, so either we know that they have liked some items, or we have rating data, then we would perform collaborative filtering. Okay. All right. So all of this falls under the association section, where we're trying to determine relationships between rows and columns of the data. And then we did talk about this small section called dimensionality reduction here, which is actually a pre-processing step, but this is when we want to purely define relationships between just the columns. So we would either perform PCA if we want to reduce the noise. If we just want to reduce the noise in the data set, too many columns, and we have a reason to believe that there is some linear relationship between them, then you can apply PCA. But if we think that some of the columns are actually derived by some other root cause or some other factor, and we're trying to determine root cause, then we would perform factor analysis. So this is all under the unsupervised learning part of predictive data science, right? We're talking about the second part of data science here. Now today what we're going to do is we're going to say, okay, what if we have already done the predictive data science piece? So we have already built some predictions, and now we are trying to go down the prescriptive data science. We're trying to make a decision, okay? So whenever we're trying to make a decision on the prescriptive data science space, then there are, it's also known as operations research, sometimes known as decision optimization. And so today we are going to do one of these, and then once we are done, we're going to come back and fill out this chart for that. Okay. All right. So let's take a look at the data, and then come back and try to define what this problem we're talking about today. Okay. All right. So let's see. All right. So we have data, shipping data. We have shipping data and supply data. So let's take a look at what we are getting from the supply data. Okay, so in the supply data file, what we are seeing is, let's see the supply data. Okay, so here we have 8 cities. Okay, you have Phoenix, Austin, Gainesville, LA, Dallas, Chicago, Atlanta, and New York. And each of these cities has some demand and supply that they can provide. So whenever you see a positive number here, that means this city can produce these. So let's say that here we're talking about, barrels of or we're talking about, tons of some sort of product, right? Let's just say we're talking about tons of oil. So we're talking about 700 tons of oil can be produced in Phoenix, 200 tons in Austin, 200 tons in Gainesville. And then whenever you see a negative number, that means they actually do not supply, but they have demand. So negative means a demand. So LA consumes 200, Dallas consumes 300, Chicago consumes 200, Atlanta consumes 150, and JFK consumes 250. So in this one column, we have information about how many tons of oil that each one of these cities can produce. Okay, and when it's negative, it's consumed. All right, so that's one data set that we have. And we also, so by the way, that data set is something, this is the output of the predictive model, okay? So the predictive model is telling us that we've already run a prediction, and we predict that for the next month, we need to provide, we need to somehow get 200 tons to LA and 300 tons to Dallas, right? And all. So this is all the output of the predictive model. But now we can't stop there. In the third part of data science, we actually need to make a decision. So what is that decision that we're trying to make? Let's take a look at what other data we have. So there's this ship data file. So this ship data file, we see that for shipping product from Phoenix to Chicago, it's they can ship 200 tons from Phoenix to Chicago, and it costs maybe $6,000 or $6,000 per ton. Okay, and for shipping from Phoenix to Atlanta, it costs $7,000 per ton because it's a little further away. But the capacity on that leg, right, on that connection is 200, right? So basically, the capacity on any one of them is 200. So think of this as like maybe a shipment of oil that can take 200 tons. One of those shipments, and it costs so much per. This is a per ton cost. Okay, so as you can see, Phoenix can. So not every city can ship to every other city. Okay, that's one interesting thing we're seeing. So Phoenix can only go to Chicago, Atlanta, Dallas, and LA. Austin can go to LA, Dallas, as well as and Atlanta. Gainesville can also go to JFK. Phoenix and Atlanta, Austin both cannot go to JFK, and so on and so forth. Right. And another thing we would see is, do you remember that here? Dallas was actually a demand location, right? They could consume 300. They have a demand of 300. But if you see here, Dallas can also ship out to Chicago and to New York and to Atlanta, which means that Dallas not only can get product, it can also ship product. And similarly, we see that Atlanta has demand, but Atlanta can also ship outside. So Phoenix, Austin, and Gainesville are kind of like your sources. Think of them like your manufacturing locations. Dallas and Atlanta are kind of like warehouses, but they also can consume some of the demand. Okay, so let's draw all this out and see what are we trying to decide. So if we go back here and let me do my best attempt at a map. So if we have the United States kind of like this, and then we've got go down to Texas this way, and then go down to Florida, kind of like that. Hopefully you get this. Okay, and something like that. All right, so we know that, so let me put all of my supply locations in blue. So I've got Phoenix here. So I've got, this is my supply location, Phoenix. And I also have supply coming from Austin. And I have supply coming from Gainesville. Okay. Phoenix can supply 700, Austin can supply 200, and Gainesville can supply 200, right? Maybe it will help if I split this. So if I put this here and, yeah, okay. So let's see if I can split the screen a little better here. All right, this will give us a little more space. All right, so here, now let's put the other cities up here. We've got LA, Dallas, Atlanta, New York. Let's put them in green. So we have, so I'll put my demand in green. So I've got LA with a demand of 200. On the other side. So LA needs 200. Dallas needs 300. Right? So we'll just put that here. Dallas needs 300. And then Atlanta is only 150. Chicago 200 and New York 250. So let's say here somewhere, Chicago 200 and New York JFK 250. Okay, so these are the supply and demand locations. And now if we take a look at the actual shipping data, let's put that here. Okay, so we'll remember that not every, you can't ship from anywhere to anywhere. You do actually need to follow some, there's only certain, so Phoenix can go to Chicago, Atlanta, Dallas, and LA. Okay, so Phoenix can go to LA, Chicago, Dallas, and Atlanta. Okay, so it can go to Dallas and Atlanta. Then, so similarly, let's draw the others. Austin can go to LA, Dallas, and Atlanta. Austin can go to LA, Dallas, and Atlanta. And then Gainesville can go to Dallas, Atlanta, JFK. So Gainesville can go Dallas, Atlanta, JFK. And then Dallas itself, even though it's a consumption location, it can go to LA, Chicago, and JFK. LA, Chicago, JFK. And then Atlanta can go to JFK, Chicago, and Dallas. So you see that Dallas can also go to Atlanta, and Atlanta can go back to Dallas. So you have sort of, two lines here. And then, so Atlanta can go to Dallas, Atlanta goes to Chicago, and Atlanta goes to JFK. Okay, so you see that all of these lanes for shipping are available. They all have a capacity of 200, and then there's a certain cost associated with every one of these lanes. So the question comes up is, the big question is, right, how much should be shipped from the from each node. So we're going to call all of these as nodes. Okay, so some of them are supply nodes from each node, so that supply and demand are met. That means, you can't exceed supply, you should meet demand at a minimum cost. Okay, so now you see how this cost is probably maybe an output of a predicted model. The demand is probably also an output of a predicted model. Supply. So this is all post prediction. Now we've taken all of that predicted output, and now we're trying to make a decision. Okay, so we're going to do a little bit of math here to try to formulate this problem as a math problem. We're going to write them out analytically, and then we're going to go back into Python to try to solve it. Okay. So let's write this out as our math problem, okay? And some of you, this might be the first time you're seeing mathematical modeling. That's okay. You can come back and watch the video again. Those of you that have already done some, taken either optimization or taken operations research, you will already be familiar with this. So let's go ahead and get started. Let's first define, so this is our mathematical model. Okay, so first we want to, we have a list of our nodes, right? We have our nodes. Our nodes are Phoenix, all the cities, Phoenix, Austin, Gainesville, Dallas, and Dallas, Atlanta. These are just the supply nodes, but then we also have the demand nodes. So I think we could go here. So Phoenix, Austin, Gainesville, Dallas, Atlanta, LAX, Chicago, and JFK. So this is all of our nodes. Okay, we're going to call these as nodes. And then if we look at the actual shipping, right, we're going to make a set of origins and destinations, okay? So all the places from which you can send stuff, okay? You can send, if you look at the Excel sheet on the right side, everything that is in column A are the origin locations. So we have from where you can send stuff: Phoenix, Austin, Gainesville, Dallas, and Atlanta. These are the places you can send stuff from. And then destinations or everything on column B. You can send to Chicago, Atlanta, Dallas, LA, so Chicago, Atlanta, Dallas, LA. So I'm trying to find all the unique ones, right? And then JFK. So did I get all of them? Chicago, Atlanta, Dallas, LA, JFK. Yeah. Okay. All right. You notice that Phoenix, Austin, and Gainesville are not in the destination list, right? And then Dallas and Atlanta are in both, right? You have Dallas and Atlanta here and here. Phoenix, Austin, and Gainesville are pure origins. Chicago, LA, and JFK are pure destinations, but then Dallas and Atlanta are both origins and destinations because you can basically ship stuff to them and you can ship from there as well. All right, so we have nodes, origin, and destinations. And now we have some data that we have got from our predicted, predictive models. We have, well, first let's go back here. For each one of our nodes, we have supply. So supply, we have supply for every node. So I'm going to put a small n here, right? We have supply that we are going to get from this sheet here on the right. And we also have, what other data do we have? We have, from the shipping data, we have capacity. And capacity we have from every origin to every destination. So we'll say from O to D. Okay, from every origin to every destination, we have capacity, and we also have cost from every origin to every destination. Okay, so hopefully everybody's with me here. And what we're trying to get here, what we're trying to figure out is X is how much. So let's just define this. This is supply at node N, capacity, shipping capacity from origin O to destination D, and this is cost per unit shipped from origin O to destination D. Okay, so what are we trying to figure out? What is our primary variable we're trying to figure out is XOD. It is the amount shipped from origin O to destination D, right? That's what we're trying to figure out. So in in optimization or prescriptive data science terms, in terminology, this would be called, these would be called sets. These would be called parameters because we already know them, and this is the output of the previous stage, and this is our variable or decision variable. Okay, this is our decision variable. Okay, now we are going to write out the actual model now that we have the notation down. So what we're going to do, what we want to do is, suppose we knew what our X was, we want to multiply that by the cost. So cost for every OD times X. This is the total cost of all the shipments. Suppose I knew my X, cost times X gives me the total cost, and then I want to sum this over all my origins, and I want to sum it over all of my destinations, right? So this gives me my total cost. Okay, so this is my total cost, and I want to minimize my total cost, right? But then I have some constraints. My first constraint is that I need to meet demand, and I cannot exceed supply. Okay, so or actually, let's do the capacity constraint first. So we know that the amount that can be shipped from any origin to any destination cannot exceed, should be less than or equal to the capacity between the origin and that destination. Okay? We know that that's a constraint, so we're going to say these are my constraints such that my capacity constraint is satisfied, and this has to be satisfied for all origins and destinations combinations. Okay, but remember that, by the way, not all nodes can go to every node, so this is, of course, whatever is feasible only. Okay, let me just put that here because that's going to come back later. All right, then the other constraint is that we need to meet the supply and demand constraints, right? So if we think of, there are many ways to write that, but think of a specific node. Let's look at, say, Dallas as a node. Okay, so you have stuff coming in from Austin, right? And Phoenix can send to Dallas. Yep. And what else? Austin can send into Dallas. Phoenix can send into Dallas. And Gainesville can send into Dallas, as well as we said that even Atlanta can send into Dallas. Right? So we have 4 sources of product into Dallas, and then from Dallas you can go to LA. That's out. Go to LA. You can go to Chicago. You can go to JFK, and you can go back to Atlanta. So if we look at one specific location like Dallas, we should be able to say that everything, everything going into Dallas, total into Dallas, right, minus total out, actually, let's write this the other way. Total out of Dallas minus the total in to Dallas should be equal to the supply at Dallas. Let's see if that makes sense. So everything going out of Dallas. So this is Dallas to LA plus Dallas to Chicago plus Dallas to JFK and Dallas to Atlanta. This all the stuff that's going out, right? Minus everything that's coming into Dallas. So you have Austin to Dallas. Then you also have Phoenix to Dallas. And then you have Gainesville to Dallas. And then you have Atlanta to Dallas. These are the 4 sources that you can come in. So everything that's going out of Dallas minus everything that's coming into Dallas should be equal to the supply, right? Because if there's more going out of Dallas, but it is consuming some, then the remaining should be the supply, right? And if this is not clear, just think about it for longer, and if you write it out, you'll start to see that, right? So think of this kind of like, flow conservation. Even in physics, you have flow conservation that it needs to even out. So here, what we're saying is that anything that comes out minus everything that goes in should be equal to the supply. And because supply is also, the negative supply is demand, it kind of works out. So if there's, less going out and more coming in, that means this value will be negative, which means it should be equal to the negative values of supply, which is demand, right? So how do we write that as a constraint now? If we come back here and we want to write that as a constraint, let's see. So we want to be a little, creative with the way we write this. So we said everything. We said here everything going out of a city, right? So let's say we have a specific city or specific node n, okay? And I'm going to pick a specific destination, and I'm going to sum over all the destinations. So this is, think of n as Dallas, and from n, I'm going to go to, and I'm going to write this for all n, okay? So here, we're looking at this here. For each one of these nodes on the right, Phoenix, Austin, Gainesville. So let's look at Dallas here. So from Dallas, all the cities we could be going to, all the destinations. So this is the sum of everything going out of Dallas. And if we subtract from that, the sum of everything coming into Dallas, okay? So here now, Dallas is the destination, and from all the different origins, we're going to come in to Dallas, and we're going to sum over all the origins, right? So this part is giving me everything total out. This is total out of node n. This is total into n, right? And this should be equal to the supply at n. Okay, so again, this is known as the flow conservation constraint, and so between these constraints, and of course, we're not going to allow our x has to be, this value should always be greater than or equal to 0, because you can't ship negative values. And so this is what we would call a mathematical model. Okay, so this is our mathematical model, and this is what we want to codify. Okay, and now if we were to try to do this, manually, then of course we can do this, the computer science way, right? Which is saying, okay, I'm going to try I'm going to take every combination, and then I'm going to say, okay, of course the capacity is 200, so I'm going to go, 1 unit from Phoenix to all of the locations, and 2 and 3 and 4 and 5. So we can it's called total enumeration. So we can enumerate all the combinations, right? We can enumerate all the combinations. And so if we look at all the combinations we can enumerate, if we try to go down that path, then look at the right side here in our ship data, right? We basically have, how many combinations do we have? We have from Phoenix to Chicago, we can do up to 200. So that means we have to try all 200 combinations. Then Phoenix to Atlanta is another 200. Phoenix to Dallas is another 200. All the way to Atlanta to DFW, so which is 200 to the power 17. This is the total number of combinations, and that's assuming, we're not even doing fractional amounts, right? So, and if this took, right, let's just do a quick calculation here. If each calculation, if we try to do it just using straight up coding, then we say 200 to the power 17. I'm doing this off on my calculator. And let's say that it takes 1 second to do each one of these calculations. So we're going to divide this by 3,600 seconds per hour times 24 hours times 365 days. Okay, let's do that just to see how many days in a year. So how long would it take to do this? So divide this by 3,600, then divided by 24, and divided by 365. So it would take approximately 4.15 times 10 to the 31 years to go through all the combinations. And needless to say, that's a little bit beyond our lifespans. So what's a better way to do this? So this is where prescriptive data science comes in. So in prescriptive data science, we use optimization methodologies. Okay? So we use optimization methodologies to say that, all right, so we use optimization methodologies to solve this, and essentially it's, instead of going through all the different combinations, what happens is it has intelligent, so operations research is what this area is typically called, or optimization, and in this area we find intelligent ways to search for to survey the search space, okay, the search space. And so we don't look at every combination. And so there are intelligent ways to say, if this is where all the different options are, then it'll look at a small location and then say, oh, you know what, it's going to have to be somewhere here or here or here. So you don't have to look at all of these spaces. You don't have to look at, all of these areas. So it intelligently knows where to look for the optimal solution. Okay, and if you want to know more about that, go ahead and take the prescriptive data science course, and we'll go into more details about this. But it's important to add this into your list of tools in your toolbox, because this is the third major area within the data science field. So let's go ahead and now write that out. Okay, so I'm going to try to let's see, bring this now here, and then okay, so I'm going to need to use okay, so that we can use this when we are writing this up. Let's see if I can Okay, that's better. All right, so let's go here. All right, the first thing we'll do is let us initialize our libraries. By the way, I recently started using Google Colab, which is Jupyter on Google, and it seems to be pretty nice. So I guess we can try that sometime also. Okay, we've got pandas. We'll come back and add some other libraries later that we might need. So let's go ahead and load data. We already have the two data sets we've identified. So we've got the supply data and read CSV. So data shipping supply data CSV. And if we bring up that file for a second, so let's look at what it does. And let's look at supply data. So this is what we would have expected, but I'd like to, because I'm going to be using the nodes in my I'm going to use them as my sets. I'm going to actually tell pandas to use the node column as my index. Okay, so that means use the first column as my index. So that would be index call and give it the column number. Of course, it starts at 0. So now you see that it would use this as my index, and I'm going to use this later on, right? This is our list of nodes. So this is a nice way to get the sets from the data set directly. For those of you who have already done optimization before, this is a nice little trick, okay? Which I haven't really seen very much out there, so it's good to know. All right, and then if I'm doing ship data, I've got my ship data file, but notice that in my ship data, I actually have, so if I take this out, okay, my ship data, I have origins and destinations and then capacity and cost. So I would actually like to use both of these as indices, because these are my origins and these are my destinations. And so I want to use both of these columns. So I could do index call equals, you guessed it, 0, 1. Okay? Use both of them. And now you will see that just from the shipping data, I'm able to pull out all of my origins and destinations, right? So remember, we defined our nodes. This is going to help us in that. Okay? This index conversion. All right, so let's go back. We've got this. And now we're going to go ahead and build our optimization model. This is the first time we're doing something in the prescriptive arm of data science. Right. So first, let's define our, let's see, sets, parameters and variables. That's this section here. So there, what we'll do is, all right, let's start with sets. So we need a set, you see on the right side, we need a set of nodes, set of origin and destination. So let's start with nodes. Let me give it a name n for my nodes. And because I have my supply data, remember that these are my nodes. So I'm just going to say supply data index. That should give me my nodes. Let's check. Yep, that gave me all of my nodes. Now let's do same way. Let's do origins. So this is my set of nodes. Here for my origins and destinations are both from ship data. So if I bring that, so ship data, my first index is my origins and my second index is my destinations. So origins, if I say ship data index, but then I want to tell it that it's the first one, right? So this is, you can do it using levels, and then say my first level. By the way, this is very useful. Whenever you pull data sometimes from APIs, you will see that data comes in levels. And so it's good to know how to access data at different levels. So let's see if that works. Okay, so all of my origins are Phoenix, Austin, Gainesville, Dallas, and Atlanta. Phoenix, Austin, Dallas, Gainesville, and Atlanta. It ordered it in alphabetical order here. All right, and then destinations is the same as origins, but it's our index levels is 1 now, and let's give it a name D. Okay, so this is set of all nodes. This is the subset of origin nodes, and this is subset of destination nodes. Okay, all right. Okay, destination nodes are Atlanta, Dallas, JFK, LA, and Chicago. Good. And remember that our variable X is over all origins and destinations. So every origin destination combination, that means for every one of these combinations, we're going to have, think of another column X that we're trying to figure out, right? We're trying to figure out what that should be. How much should be shipped? You can ship to 100. How much should you actually ship? So X is going to be defined over origins and destinations. But you see that not all origins can go to all destinations, only these combinations, right? So it'd be nice to create a combination of OD, which is each one of these combinations. So let's create another set called OD. And for this, I can just say ship data.index. It will take both 0 and 1. Let's look at that. So this is basically each one of these. Okay? Phoenix to Chicago, Phoenix to Atlanta, Phoenix to DF. Yeah, so that's what you're seeing. Chicago, Atlanta, DF. So it's every combination. And this is what our X is going to be defined over. So this is, so like I said, this is a very efficient, clean way to get sets from your data directly without writing a lot of code, okay? And without having to define it specifically. All right. So we got that, and now let us do our parameters. Remember, parameters are the stuff that we got from the previous stage of predictive data science. We've got supply, capacity, and cost. So we can define supply as supply data, and if we look at that data frame, the column is called supply, so we can just say supply data dot loc, all rows, and the column is supply. Right, so let's just check and make sure that it looks okay. All right, here's my supply data frame. I mean, you didn't have to do this, I guess, you know, the supply entire data file itself is that way, but this is for completeness. And then let's do cost is ship data dot loc, and let's go there and see what that looks like. Okay, so cost is ship data dot loc, all rows and cost, and then the capacity is also ship data dot loc, and okay, so I'm getting these three parameters from the two data files we have. Right, just check capacity, cost to see if that good. Okay, we pulled that out. Good. All right, so we've got our parameters, and now let's define our variable. So we said that our variable is X, and X has to be defined over all OD combinations, right? But how do we do that? And for this now, we need to start getting into a new library that can do mathematical optimization. So if we look, by the way, this is going to be, you see that here, this is all linear. There's no non-linearity here. You just have the variable here and something multiplied by it. You don't have the variable squared or the variable multiplied by itself. So that would be considered linear optimization. So let's look for Python linear programming. This area is called linear programming. So there's SciPy has something called linprog, but there is another one that I like to use. Let's see if there's. Yeah, so here this is called pulp. Okay, and this is a very useful library that we can use, and it's open source. A lot of this, by the way, needs solvers, but it can do it open source, which is nice. So you would need to pip install pulp to be able to use this, which I'm gonna put here. Say that's what you would need to do, but then I'm going to go ahead and import pulp. Okay. Now I need to define my variable. So this is going to be my variable section. And so X is LP variable, and then we define what it is, and then you give it give it a range, okay? And so I'm going to breeze through some of this. You can go into this in detail, but I'm going to call my variable X, and then this is a .lp variable. That's the name of the variable. Okay, the label was X, and here I want to define X over a certain range. So I'm going to do that here. OD, it's going to be defined over OND. It's not just one value. For O and D in OD. So what this is basically saying is that I am defining my X variable here. I'm defining my X variable, and I'm saying that it can have two indices, O and D, and what is the range of that? For O and D, for every combination in this OD set. Okay, that's how you read this. So if I had a variable that was only nodes, it would say N, for N in uppercase N, right? That's how. So this is a way to define this here. XOD is the amount shipped, and then I want to say that it is it has a lower bound of that means it can't be negative. So we'll say lower bound is 0, and this is something that tells you whether it is your X can take continuous or discrete values. So here we're going to say continuous. That means X can take fractional values if necessary. Okay, but if you were doing something like number of people, right? If we were shipping people, then we wouldn't do continuous. Right? Although theoretically it would have still worked, but that's for a different conversation. All right, so let's see. Did we miss something here? Right. Let's see, load bound. Oh, because we are actually giving a list, we should give it a dictionary. Okay, this is a set of values of X, not just one. So let's try that. Okay, so now we have X. So let's just take a look at what X looks like. So this is basically, you see that for every combination of origin destination, it is going to assign some value at some point in time, right? It doesn't know what the value is at the moment. So we're going to try to figure this out. All right, so we have our variables, sets, parameters, and variables. Now we're going to define the model itself. So let's just say this is the model now. I'm going to be building the model. The first thing is we want to just set up or define the model. Remember, like we did in all the other machine learning models we were doing, we were defining it, although here the way we're going to define it is slightly different. So let's see. Okay, so that's, you say LP.problem. Okay, this is how you define the model here. Okay, so maybe we'll call this, I'll just call this model, call it model LP for shipping. Okay, that's the model we have, and this is a pulp LP problem, and we can give it a name so that we can use it, later on. Cost minimizing network flow problem. This is just a name for us to know what it does, and then we were going to say this is a minimization problem, so we can define that here and say that this is pulp.lp minimize. That means I am going to be minimizing once I set this up. Okay, so I've defined this. Yeah, it doesn't like spaces in the name, but okay. So now I'm going to be adding the objective function. I'm going to add these equations in, I'm going to add these, I'm going to add these, and I'm going to do it by saying something like this. So define model, specify objective. So when I want to specify the objective, I'm going to say model plus equals. That means I'm going to be adding some equations into this model. Okay. And now remember, I want to do sum of cost times x, right? Or x times cost. So I'm going to say cost of OD times x OD. Okay, so I know that, but then I need to do this over all origins and destinations. So in pulp, you do summation. I don't know if they have it here. In the syntax, you can call the sum function. They have a sum function. I'm going to go ahead and use a sum function. You can go into the documentation later. So it's called, let's see, pulp dot, let's see, for sum, right here, LP sum. So I want to sum this. I want to sum this over for, remember I want to do it for O and D, right? For all O and D in OD. Okay, so for all OD combinations, I'm going to multiply the cost times X. Okay, so I've specified my objective, so I've got this part. Now I need to add my constraints. Let me add my, so to specify objective, then add the, say specify the capacity constraint. So we'll say model LP shipping. I'm going to add another set now here. I'm going to say XOD. XOD has to be less than or equal to the capacity, right? And we already defined capacity here. And that is also over O and D. Okay. Oh, sorry. Okay. Okay, so what's happening here? Okay. Let's see for, oh, so yeah, because we have to write this constraint for every O and D combination, we need to say that. So for OD in OD, you need one constraint each, right? Because you remember we said for all O and D, this is the for all O and D part. Okay, so we do that. And actually, it is best practice to make sure that, okay, no, that's fine. That should be okay. All right. And then let's also specify the demand, the supply / demand constraint, right? Because they're both together, which is the second one here. And this we got to be a little careful because we're going to be summing up over. So this is for n in all nodes, right? We're doing this for all nodes. And then I'm going to do model DL shift plus equals, and we're going to do sum. So let me do sum here. Bring the sum here. Now I'm going to sum x n d. Okay. And I'm going to sum it over all d. Okay. For d in d. That's what I've got here. Minus, and then I'm going to do, this is everything that goes out minus everything that goes in. So in, I'm going to iterate over all the origins to this same node for O in O. And this needs to be equal to supply at n. Okay, so we're writing this exactly like we did here. Okay, so we're getting an error here. So Phoenix to JFK, it can't define Phoenix to JFK. Let's look at the data. Oh, so interesting. So it can do Phoenix to Chicago, Atlanta, DFW, and LAX. And it can't find Phoenix to JFK here. So it's saying, what should I do for Phoenix to JFK? So what we realized here is that only certain origins and destinations are feasible, right? Phoenix doesn't even go to JFK. So whenever we hit that combination, because we're saying go to all destinations, go to all origins, some of those combinations are not feasible. So what we need to do is replace infeasible values with 0, okay? Just to make it work. So we could do, that's done using the .get function. We can say x .get whenever you say, so nd, so try nd, try to get nd, otherwise replace it with a 0. Okay, that's get, yeah. So you can do try to get nd, otherwise replace it with a 0. Okay, let's do the same thing here. Get values O and N. And if you can't find ON, if that doesn't exist, then replace it with a 0. Okay. All right. So now it works because it's not worried about infeasible combinations. All right. So we've defined the supply and demand constraint. And now we just need to run the model. So run the model. Let's see if we have some syntax here to see how to run it. Yeah, so the model name .solve is what we're going to call, and then we can figure out what the status is. Did it solve it properly? We can just call the LP status function. Okay, so let's do model LP shift.solve, and let us try to get the status. Status. Okay, so I think I need to display the status, so that should be quote.lp status is what they called it, and I need to give the name of that status. There you go. Okay, so this tells us that it has been solved out. You see that click of a button. What was it? Fraction of a second. And we went back here and said if we would try to all combinations, it would take so many years, right? So you see that just by applying intelligent ways, we'd be able to survey and find the best solution. Let's see what that solution is. So let's take a look at the results here. Okay, let's say, so I think it's, yeah, so value is what it sets, is what you need to call to figure out what X is. So we'd say, first of all, let's see what the objective value is. So yeah, objective. And what is the value of that objective? So the value of this objective. So this is the total cost. So here on the right side, the minimum cost is 5,300. So if the units are in thousands of dollars, then this would be $5.3 million, right? All right. So this, and let's see. Let's say print cost. Okay, that's minimum cost. And now let's also see what are the results. So at the end of the day, we need to know what the X values are, right? How much should be shipped from where to where? So let's look at, let's say, this is the minimum cost, and then here we want to see what the optimal shipment selections. And so here, model.variables and DL.variables, this is all the list of variables. So and we only have one, right? So you have, oh, by the way, this is a nice way to take a look at the entire model that it wrote up, okay? So you can see cost times X from Atlanta to DFW, Atlanta to JFK. It wrote the whole objective, and here's all the constraints, right? Here's all the capacity constraints, and here's all the supply and demand constraints. So this is a nice way to take a look at the model. But if we want to see what the values are, let's say for V in all of the variables, what I want to do is I want to print the variable name, and I also, say equals, and then the bar value. Yeah. So the name of the variable and the value of the variable. Cool. So what we're seeing here is that you see here it says 200 units should be shipped from Austin to Dallas, Dallas to Atlanta 50, Dallas to JFK 50, and then Gainesville to JFK. So this is the best combination of amounts to be shipped. Okay. So interesting. Let's take a look at this. Austin ships 200 to Dallas. So Dallas gets 200. Dallas also gets 200 from Phoenix. Okay. So that's a total of 400 into Dallas. But if you look at the demand for Dallas had a demand of 300, but now it has got 400, right? That means it needs to shed that 100 out. So you see that from Dallas to Atlanta, it gave 50. Dallas gave away 50 to JFK. So altogether, it dropped off 100. So it came back to 300. This also shows that sometimes, let's go back here and put this on our map, okay? And that way we can take a look at, let's see, view, let's go back here, okay? All right, so let's go and then see what this looks like on the map. So here what we're saying is that 200 should be shipped from Austin to Dallas. So let me just do this in, let me just do it in red so we can see it easily. So Austin to Dallas, Austin needs to ship 200 to Dallas, okay? and then Dallas to Atlanta 50, Dallas to JFK 50. So Dallas to Atlanta 50, Dallas to JFK on this arc 50. So, all right, and then let's just complete this. Gainesville to JFK 200. So on this one, we've got 200. So Gainesville is sending all of its shipment directly to JFK, right? Which makes sense. They're on the same side of the country, and the shipping cost is probably low here. Phoenix to Atlanta is 100. So Phoenix is actually shipping all the way to Atlanta, right? So that's happening, and shipping 100 there. Phoenix to Dallas is 200. So Phoenix is shipping 200 to Dallas. And then Phoenix to LA is 200. Remember, Phoenix has a big supply, right? So Phoenix to LA is 200. So LA gets its full amount from Phoenix. JFK gets its full amount from Gainesville, which is what we would have expected. And then Phoenix to Chicago is 200. So Phoenix also sends the full amount to Chicago. So what we are seeing here is that, instead of so JFK needed an extra 50, right? So Atlanta could have sent that to JFK, but because Austin was so close to Dallas, and Austin was able to send extra to Dallas, and then Dallas shipped the additional 50 to JFK, and Atlanta also needed an extra 50, so that extra came in through Dallas. So the nice thing here is that our mathematical model was able to figure out the optimal. So here's the aha moment, right? Is that the mathematical model is able to comes up with intelligent and intuitive combinations, right? We may not have thought that Dallas could have been used as a what is called in supply chain. This is also known as a transshipment center, and these are called transshipment centers. So we would have not thought of using Dallas like that, but because Dallas has the ability to ship out, the model automatically use that. So so hopefully through this exercise, we're able to understand the power of prescriptive data science. And prescriptive data science is essentially the next phase of where the industry is going. You see lots of companies hiring what they call chief decision scientists, who are people who are in the prescriptive arm of data science. Okay, so let's go ahead now and add this to our cheat sheet here. That we've done all of this on the bottom for predictive. Let's do some for prescriptive also. So I'm going to move this out here. This was the pre-processing stuff we had written previously. Okay, so we know that this whole section on the bottom here is related to predictive data science. For prescriptive, some of this might be a little over the top, but for completeness, again, I'm going to show it to you. So this area, so prescriptive data science is also known as, like I said, decision optimization. So whenever you're in the prescriptive data science area, if you have an analytical, so if you say that I do have an analytical model, so analytical model exists, so you can write the model mathematically like we did today. Then you go down the path of mathematical programming. Okay, you go down the path of mathematical programming. And if an analytical model does not exist, that means it's too complex to build. And analytical model is too complex. then you could resort to simulation, even for making a decision. Okay, so you could use simulation for predictive, but you could also use simulation for prescriptive. Now, within mathematical programming, if your parameters are fixed, so if your parameters are fixed, that means they were already determined in a previous stage. Like for us, that means it was not like a distribution or something. So our cost, our supply demand, those are all fixed and already predicted. And then we would go down the path of deterministic models, and which is the path we went down today. And within deterministic models, if all of if all of the objective and constraints and everything are linear, like we saw today, if everything is, so you have here, you can say linear programming is finally what we did today, but you can have also had nonlinear programming, if you had nonlinearity in there, or integer programming if you have only integers. Okay, so it's only discrete. So those are deterministic models. But if the parameters are not fixed, so parameters vary, okay, and we have some sort of distributions for them, this is when you can start to build stochastic models. Okay, and then within stochastic models, you've got if time is discrete, then you would build discrete time Markov chains. I know that this is all more than what this class takes, but just in case you don't end up taking the other prescriptive data science class, at least this you can keep this with you. Discrete time Markov chains, and if time is continuous, then you would build continuous time Markov chains. Okay, so and this is all what we would go over in the other class. But there is an interesting sort of connection here that I wanted to call out. You see how in mathematical programming today, we made all the decisions all at one time, right? We have the entire next month. We know all the demand. We know all the capacity. We know all of that. That's why we went down the mathematical program. But what if we had the capability to just make one decision at a time? Right? Think of like a game where you just need to you're playing with somebody else, or there's other players in the market, and you want to optimize the next step. You want to keep the future steps in mind, but you can only take one decision at a time. You can't take all decisions. If that's the case, if the decisions can be made one at a time, okay, then that's another type of mathematical programming. So decisions made one at a time, and this is called dynamic programming. Okay, and this is another area of mathematical programming, but the reason I call it out here is because even from predictive data science, there is even from unsupervised learning, there is another arm. So we said, you have clustering, you have dimensional reduction, you have association, but this dynamic programming is something that even unsupervised learning players play, and it's the exact same thing, but they call it reinforcement learning. Okay, so these dynamic programming and reinforcement learning are the exact same thing. All right, and this is related to unsupervised learning. So that's the main connection between unsupervised learning and mathematical programming. But when you look at it from the mathematical programming side, it's actually when you're making one decision at a time. And from the unsupervised learning side, you are basically it's unsupervised because you have no idea what is a good move versus a bad move, because you really and you need to kind of reinforce yourself. So when you take a decision, or when you make a move, then you learn whether, based on what happens, whether you win or lose, you realize whether that move was good or not, right? So so dynamic programming from mathematical programming side is the same as reinforcement learning from unsupervised learning. And by the way, this area of dynamic programming / reinforcement learning has a few tools of its own. Those are called. I'm just going to write those out here. So one is called. You can solve that using deep Q networks, or you can also use something called SARSA. If you ever have to do that, you know that those are the tools you need to use. Okay. All right. So a lot of content here, and this is but hopefully this gives you a cheat sheet of when you are in playing with data, you are given data, or you go get data, you should first of all know that you should do a significant amount of descriptive data science, using either tooling like Power BI. Either way, you should always do a lot of EDA. And then once you have a good idea, you can go down the predictive data science path next. And once you go there, typically you would start with unsupervised learning because you don't really have much labeled data. But then at some point in time, you might have more labeled, then you can go down the supervised learning path. And then when you have a prediction, in many cases, maybe the prediction is the end of the road, but in some cases, you have to make some very big decisions. And that's when you go down to the prescriptive data science arm, take your predictions from before, try to build an analytical model. If you can't, you can go down simulation. If not, if you can, build your math programming model, and then try to go solve it using the libraries we just talked about today. Okay. All right. So that essentially wraps up the theoretical part of this course. And so those of you who are actually attending this live, we will be moving into the capstone part of this course next. But that essentially wraps things up. And so thank you very much.